Hello and welcome back. This is Chapter 18 in versions 1 and 2 of the Klein text and Chapter 17 in version 3 of the Klein text. So we're going to talk about reactions at the benzylic position to finish up this chapter. And there really isn't a lot left in this chapter, but I didn't want to overwhelm you by putting this into the previous video. Okay, so remember that benzene rings themselves aren't particularly reactive. We're going to see how we can do some reactions on them in the next chapter, but the benzylic position is particularly reactive, just like allylic positions are, but even more so than allylic, because being next to a benzene ring provides particular stability. Okay? So aromatic rings and alkyl groups are not easily oxidized, like with sodium dichromate or the Jones reagent. But if we have a benzylic position, so remember benzylic, what does that mean? That means we have a benzene ring, and the benzylic position is one carbon over from a benzene ring. By the way, a benzene ring attached to something else is called a phenyl group, and a benzene ring with an extra carbon is called a benzyl group. Okay, and that's because it has a benzylic position. Okay, so this benzylic position is particularly reactive. I'm going to erase all this. So if you use something like sodium dichromate, you can react at that benzylic position to give you a benzoic acid. It's so reactive that it can be fully oxidized and lose every other thing that's attached to it in the form of a carbon. But in order to get this reaction to go, you actually have to have a hydrogen on here. If there's no hydrogen at the benzylic position, you don't get a reaction. So you get no reaction if there's no hydrogen. So if you get that oxidation, it actually will knock off the other things that are attached at that position, and you can do that with the Jones reagent, sodium dichromate, or you can do that with potassium permanganate as well. Okay, so that will also give you the what essentially is a carboxylic acid. So in this case we need to protonate in order to get our acid out with the potassium permanganate, but with the Jones reagent we can run that in the presence of sulfuric acid, and we get the acid functional group at the carbon of the benzylic position. Alright, and so both of these are in fact benzylic positions, and they both have hydrogens on them. So this has one hydrogen, this has three hydrogens because it's just a methyl group, and so they can actually both be oxidized with Jones reagent. And we can see there's some other reactions we can do at that position as well. If we use NBS or BR2, NBS in heat, BR2 in light, we can actually get bromination at that position, so we can get a bromine on there. Okay, and you've seen a lot of these different reactions, so I'm not going to go into a lot of detail here. With water, you can get an SN1 reaction, okay, giving us an OH group here. With hydroxide, you can get an SN2 reaction, giving us a substituting bromine for, say, hydroxide. Okay, and we can go on with a strong base. We can get an elimination reaction by E2, okay, or with sulfuric acid, we can get an elimination as well. So you've seen all of these reactions before, so I'm not going to go into a lot of details on that. Okay, so let's draw the expected product when each of the following is oxidized with chromic acid. Okay, so that would be like the Jones reagent. So for A, remember we've got this benzylic position here. Okay, so here's our benzylic position. So we're going to oxidize with chromic acid. What does that mean? We're going to get a carboxylic acid on here, so we're going to have benzoic acid. So what about this one? We have a benzylic position here for B, and we have a benzylic position here. As long as those positions have hydrogens on them, a hydrogen on them, we're going to replace that whole thing with a acid functional group. Okay, so there we lose the carbon that was on there, and for this one we're also going to get an acid functional group. Okay, so for the next one, the question is for C whether we have a hydrogen at that position. So we have a hydrogen here, we have 2 hydrogens here, we have no hydrogens here. It's a quaternary carbon, so we can't get a reaction here. Okay, we're only going to get a reaction here and here, so let's draw our product. So it's going to kick everything else off, and we get the acid group, and we kick the methyl group, the extra methyl group off here, we get an acid group, but for this one we still have our T-butyl group. Alright, so we can get all of these reactions. We can get radical bromination. We can go on to get an SN1 or SN2 reaction at that position. Oxidation, radical bromination, E1 or E2, SN1, you know, different reactions that you've already seen before. All of these can happen readily at the benzylic position. Okay, so giving the reagents necessary, so I may just let you guys do this, right? So how would you go from here to here? So NBS and heat, okay? How would you go from here to here? A strong base. How would you go from here to here? An oxidizing agent like Jones. How would you go from here to here? Oxidizing agent, so let's just pick a different one, KMnO4, okay? So, it doesn't look very good. KMnO4. Okay. So, all of those reactions are possible. We can also do a reduction if you use something like H2 and nickel, H2 and platinum. It's very difficult to achieve, though, and you have to use high pressure and high temperature. Okay? So, generally, at regular atmospheric pressure, you're only going to reduce a side group, say, you're not going to reduce the benzene ring. Now, there's another reaction that we can use to get this reduction, and that's similar to the reaction that we saw for an alkyne. So remember the alkyne reduction where we had, let's do one like this, sodium in liquid ammonia. What did we get? We got the transalkene. Okay, so that was also a reduction reaction. This reduction with benzene is called a Birch reduction. That's specific for benzene. Okay, so in the first step of this mechanism, the sodium is going to donate an electron in to the pi system, forming a radical anion. So we have a radical here and an anion here. That anion, being negatively charged, is strongly basic and can pull a hydrogen off of the methanol that we in fact have in solution in this case. Okay, and so methanol donates a hydrogen there. Okay, and so the next step, we still have this radical left. So sodium donates an electron to the radical because that's unstable. And then that anion can pick up another hydrogen from another methanol molecule, reducing the benzene ring overall to this these unconjugated double bonds. Okay, now we have two sp3 hybridized carbons opposite each other. And that's called a Birch reduction. Well, it turns out if we have an electron donating group on the ring, so this thing is going to donate electron density in, we're not going to reduce at the carbon bearing that that alkyl group. Okay, we're going to reduce adjacent to the alkyl group, meaning the double bond is going to end up on the alkyl group. So we're going to reduce adjacent to the alkyl group, and that's because, remember, we have a radical anion as an intermediate in that system, and that radical anion, okay, is going to not be stabilized by an R group that's being attached. So if that R group is donating electron density into that radical anion, it's going to destabilize the radical anion, and that's not going to be stable, and so the radical anion is going to end up in the mechanism adjacent to the alkyl group, so that when it's donating electron density in, it will it will not interfere with the radical anion that forms. Okay, but if you have an electron withdrawing group, like in the case of acetophenone, what we see is that we do reduce at the carbon bearing the electron withdrawing group, and we don't reduce at the carbon adjacent to it. Okay, and that is because the electron withdrawing group is withdrawing electron density from that system, and therefore it can stabilize the radical anion that forms as an intermediate. Okay, and so if we have an electron withdrawing group, we reduce at that carbon. If we have an electron donating group, we would reduce adjacent to that carbon. Okay, so I'm not going to go over any homework problems for my students with that, but keep that in mind in case you have some work on Wiley Plus. So I'm going to look at some synthesis problems now just to finish up this chapter. How would you go from left to right? How would you go from our starting material to our target molecule? Okay, so these are really not all that complicated. The first thing we have to do is introduce some functionality here. So we can't get a reaction if we don't have any functionality. And so the first thing we need to do is say put a bromine on there. So we can use something like MBS and heat to give us a bromine on the ring. Okay. And then to go from here, we can just use an SN1 reaction with something like water, okay, because we can't do SN2, it's too sterically hindered. Okay, so for the next one, we can do this one. We still need to introduce some functionality in order to go from starting material to product. So the first thing we're going to do, let's just use, again, NBS and heat. We could use Br2 and light. That would also work. And so that's going to put a bromine at the benzylic position. Okay, then to go to the target molecule, all we need is a base, something like sodium ethoxide. So for the next one, again, we need to introduce some functionality, so let's just use NBS and heat. Okay, and then to go from here to here, we could just use an SN2 reaction, so we can just use sodium cyanide, and that'll give us our product, okay, our target molecule. We got another one. So to go from starting material to product, this one looks a little bit hairier than it really is. So first, notice that this is a benzylic position, and we do in fact have a hydrogen on here. So let's use NBS and heat to introduce some functionality. Okay, so now we're going to put a bromine on here. And then to go from here to here, this is a CH3O. Okay, so we added a CH3O with an SN1 reaction. So we just need something like methanol, and we'll get an SN1 reaction. That bromine can be easily replaced. And the reason SN1 happens so readily at the benzylic position is because we have stabilization of that cation that forms through resonance. So you can go back and draw resonance structures for that stabilizes the carbocation that forms at that benzylic position. Okay, so I'm not going to discuss spectroscopy of aromatic compounds in this section, but I will come back and discuss that at a later time.